All right, so in that first example, we got a pretty good idea of how the mechanism of substitution works. We're trying to remove all traces of x and dx, replace them with the variable u and our du. And I alluded to the fact that sometimes getting that u correct might require trial and error on our part. So just try not to get too frustrated at first. As you do more and more of these, you're going to build some intuition, and you'll find that they go a little bit more smoothly. Now, sometimes the du step can be a little bit tricky, and in the last one it was very straightforward. If you remember from the last example, we needed to get rid of this 2x and the dx, and luckily du was 2x dx. It matched up perfectly, so it was a nice one-for-one swap that we were able to make. It's not always that easy, so I wanted to do some examples where maybe it is a little bit less direct than just a one-to-one swap. But again, it's not that bad. We just got to do a little bit of algebraic manipulations. So we've got x squared times the square root of x cubed plus 2. So I would say let's try the term under the radical and let that be our u. So I'm going to go off to the side here. I'm going to say if we let u be x cubed plus 2. And again, if you're asking why did I choose that, remember that the substitution method is the opposite of the chain rule, where we are identifying inner functions because we're dealing with the derivatives of composite functions with the chain rule. So oftentimes that inner function is what we're going to be choosing as our u in the substitution method. Now you also might notice that that was a good choice because when we go to calculate our du, what do we get? Well, we get 3x squared and then our dx. Notice this is going to work out pretty nicely because if we were to let's restate this integral here. So we've got the integral of x squared times the square root. Now we've replaced the x cubed minus, or plus 2, pardon me, with a u, but we still have that x squared dx that we're going to need to get rid of. And if we go up to our du statement, we've got 3x squared dx. So it's almost perfect. It's just this 3 that's posing a little bit of a problem, but we can handle that easily. We want what we want to replace to match up perfectly with this statement right here. So what I'm going to do here is I'm going to divide by 3. So if I divide both sides of this du statement by 3, what I'm left with is 1/3 du is equal to x squared dx. And now what we want to substitute out is there, exactly the way that we needed it. So we're going to replace that x squared dx with a 1/3 du. So now we come back down here and we've got the square root of u times 1/3 du. And now, there we go. All x's are gone, just u's and du's, and that's exactly where we want to be. I'm going to clean this up a little bit by taking that 1/3, that constant multiple, and pulling it out front. And then I'm going to rewrite that square root of u as something more easily integrable as u to the power of 1/2 du. So now we can go ahead and we can integrate. So we've got 1/3, and we're going to do the general power rule for integration. So we're going to add 1 to our exponent and then divide by that new exponent. So just so we can kind of see it, it's going to be u to the power of 3/2 divided by 3/2 plus c. And maybe you jumped straight to recognizing that this is going to be 2/3 times u to the power of 3/2 plus c. And if we were to then multiply these two fractions together, we're going to have 2/9 times u to the power of 3/2 plus c. Now it's tempting to pat ourselves on the back and walk away at this point, but remember, we want to get this back in terms of our original variable x. So that means we're going to have to substitute in for that u. And that just requires us to go back up to this statement here and say, all right, well, u is just x cubed plus 2. So let's go ahead and take care of that little detail. So this is going to be 2/9 times x cubed plus 2 to the power of 3/2 plus c. And there we go. We've got our integral. It's in terms of our original variable, and we're done. So oftentimes this step right here of manipulating the du statement to get it to match perfectly with what we need to get rid of, in this case it was the x squared dx, is something that we have to address. And we'll see that kind of pop up in most of our use substitution problems.